Yeah, welcome to my talk. I'm Martin, and I'm going to talk about lazy queue layouts of Posets today. And this is joint work with Jawairul from Amazon, Sergey from Facebook, and the two Michaels from Tübingen. I will essentially take the title and go from the back to the front. So I will first talk about basics of Posets, quickly explain what a queue layout is, and at the very end I will get to this word lazy in the title. It's essentially a strategy how to obtain queue layouts. Posets are short for partially ordered sets, and they consist of two things. So you have a set of elements, X, and these are just elements. Yeah, the only thing we care about is that it's a finite set of elements, and we have a partial order on these elements given. Here we have a slightly different definition. We have a so-called strict partial order, and it has the properties of being irreflexive, antisymmetric, transitive. What is this partial order? So when you are given two elements, two distinct elements out of this set X, you have three options. So let these two elements be U and V. So U can be less than V, V can be less than U, or you don't know. So the partial order is not giving you this information. In the former two cases, you say that these two elements are comparable, because you can compare them. And in the last case, you say that they are incomparable. Yeah, so we have this poset, and in order to get a queue layout, we need a graph. So we want to turn this poset into a DAG. And how do you do this? For the elements, this is rather easy. So every element corresponds to exactly one vertex in the graph. For the edges, you need to be a bit more careful. So you want this DAG to be some minimal representation of the posets. And what you do is you don't put an edge between every two elements that are comparable. What you do is you skip transitivity. So instead of two elements being comparable and there is an edge, you restrict yourself to a path and not necessarily an edge between them. So if U precedes V in the poset, if this is the information that you have, then you have to guarantee that there is a path from U to V. This implies, you are skipping this transitivity essentially. This means there are no transitive edges in the DAG. Yeah. So to make this more formal, what you do is you only put an edge from U to V. If of course U precedes V in the partial order, but there is no W in between. This implies then that you get this property of having a path from U to V, and that you don't have transitive edges. Another very important term is the so-called linear extension. What is a linear extension? It is essentially a linear ordering of the elements that complies with the partial order. So if the partial order says U precedes V or U is less than V, then U also precedes V in this linear ordering. If you transfer this idea to the graph, to the DAG, it's nothing else than a topological ordering of the vertices. For our results, it's very important to know what the width is of a poset, and for this we need some more terminology. Here's an example deck, and before we were just considering two elements, if they are comparable or incomparable. And you can also do this now with a subset of elements. If you have a subset for which you know that the elements are pairwise comparable, like in this example here, the blue vertices in the deck, yeah, they lie on a path. So by this idea of comparability and the existence of a path, they are pairwise comparable. In this case, you say that these elements they form a chain in the poset if they are pairwise comparable. Similarly, you can define the term anti-chain, and this is nothing else than that they are pairwise incomparable. So the red vertices here, I think you agree that if you consider them pairwise, there is no path between them. And if you now look at all the anti-chains in a poset and you take the largest one, then this size of the largest anti-chain defines the width of the poset. Here you can see that there is in fact an anti-chain of size 4, and there is not a bigger one. Yeah, you can try, but there is none. And this anti-chain defines the width of the poset. So the poset behind this deck has width 4. So once you know the width of a poset, you can do something very nice, and that is called the so-called chain decomposition. If you have a poset of width W, then you can partition the elements into W many chains. And you can also do this in polynomial time. So there's, for example, the result by Felsner et al. When I remember correctly, the runtime was something like W times n square. So it is doable, and we assume in many of our results that such a chain decomposition is given, and this chain decomposition is of course not unique. Yeah. For example, I can make this blue vertex red, and it's still a proper chain decomposition. In this example, you can also see that these chains are not necessarily paths. So a chain, if you think about it a bit in the graph, is essentially a set of paths. Yeah, it does not have to be connected, as you can see here. Okay, so yeah, so what we want to do is now we want to take this DAG and turn it into a queue layout. And this parameter of width is very central in our results. What is a queue layout? It is essentially a linear layout. So you line up the vertices from left to right. And the edges are drawn in the upper half plane. And similar to a book embedding, there is a configuration that you forbid. So what you don't want is you don't want two edges to be nesting. Here in this example, the edge 1, 4 nests the edge 2, 3. If you have such a configuration, which like here in the example is unavoidable, you want to assign these edges to different queues. Queues are a partition of the edges, which is here visualized by coloring them differently. And of course, what the objective is to use as few queues as possible. So the number of these partitions should be as small as possible. For a graph class, the number of queues you need is then called the queue number of this graph. We are here in a slightly different setting because we have directions on the edges, and this of course should be reflected by the queue layout. What we want is that the edges point from left to right, so no backward edges allowed. In other words, we want that the linear ordering in the layout from left to right is a linear extension of the underlying poset. And of course, then we are interested in how many queues do we need. You can here see that this direction of the edges makes a difference. So this is just a cycle of length 6, and with a bit of fiddling around you can manage to squeeze it into a 1 queue layout, just using 1 queue. There are no edges nesting. If you now have directions on the edges, then it may happen that you need more than 1 queue. So here you have a short path of length 2 and a long path of length 4. And no matter where you put this guy, he has to be between these two, otherwise it wouldn't be a linear extension. And no matter where you put him, there will be you will have to nest one of the other edges. So this then needs a 2 queue layout. Okay, so this is the overall plan. So we have the poset, we consider the DAG that belongs to it, and we want to squeeze the DAG into a queue layout. And we are interested in how many queues do you need. And in our paper, the important parameter is the width. There is this conjecture by Heath and Pamaraju, and they claimed back then that if you have a width W poset, then W queues are always sufficient. And at first glance, it looks like that this works always, but we were able to find a counterexample. So this we were able to show that in any linear ordering, this DAG here, which reflects a proper poset, that this DAG needs 4 queues, but it has width 3. And once you have this for width 3, then you can construct something bigger which grows in width by 1, but also the queue number grows by 1. And then you get the more general result that there is always a graph that needs 1 more queue than its width. Yeah. So the conjecture is not true. Okay. This is, of course, here on the negative side. Maybe there is also something positive, and we were then looking into how to construct orderings that do not require so many queues. And this is where the term lazy comes into play, and this has been coined by Knauer et al., I think. It's a very simple strategy. I wouldn't call it algorithm. So what you do is you start with some arbitrary first vertex of your choice. Yeah. For example, here the green guy, he's a local source, and he can be the first vertex in the linear ordering. And then you look to which chain the guy belongs to, and you continue in that chain as long as possible. So here you go to this guy. He belongs also to, he's the next guy in the green chain, you make him the second vertex, and then you go to this vertex, and then you realize, oh, I cannot put this guy into the linear layout because I first have to put this guy in. Okay, so then you are stuck in the green chain, and yeah, then you just continue in some other chain where it is possible, and apply the same thing until you get stuck again, and then you switch to another chain or back to the other where you came from. And there is a lot of arbitrary in the strategy. You can make really bad choices. The question is, how bad can it be? And we were able to show that no matter how bad your choices are, W square minus WQs are always enough. Yeah. One has to say here that W square is a natural upper bound for this problem. So the lazy strategy is a bit better than the worst case, and we were also able to show that this bound is tight. So we have an example in the paper, some construction, where essentially by making bad choices, this lazy strategy hits this bound. So this bound is really tight. Then we considered a slightly different approach, which is essentially just a modification of the lazy strategy, and this most recently used. What you do is when you have to switch chains, you define a bit more better behavior. What you say is, okay, I'm stuck in a chain, I cannot proceed here anymore. I will go back to the chain where I came from and try if I can continue there. So you always try to switch back to the most recently used chain. And it turned out that this one behaves a bit better. So you get, when you compare it to lazy, you can save a few Qs, but it is not much. So W minus 1 squared plus 1 is about W better than this one. Open problems. Of course, these two strategies are very simple, and we were able to show that the upper bound is also a tight bound. And the question is, can we close this gap between this counterexample to the conjecture and this Q number produced by the MIU strategy? I mean, this is a big gap. Of course, then the counterexample, we haven't considered if we can exploit planarity in any way. The counterexample is not planar, for sure. Question is, if you restrict it to planar posets, can you do better? And then there is also this with 3 poset problem. So we know that the counterexample has width 3, it requires 4 Qs, but can you do every width 3 poset in 4 Qs, or are there ones that require 5 Qs? Thank you very much.